Hello everyone. So in this recording, I'm going to be talking about public key cryptography. And last time, or the last recording, we were talking about the secret key cryptography, where the key has to be secret between only two parties, right? Only two people or two entities. Anything, if a third entity get the key, now we don't have uh, good cryptography anymore. We don't have good secret, right? In public key cryptography, the main point is actually the one of the keys, because we have two, one of the keys is published, is public. Everybody knows it, right? And because of that, it's also called asymmetric one versus the symmetric, which is the private key cryptography or the secret key cryptography. In this case, we have asymmetric. The reason for being or called asymmetric is because um, we have two keys. Right? Another difference is in private or secret key cryptography, the key is the same, but the algorithm for the encryption and decryptions are different. So we encrypt with one algorithm and decrypt with another. Usually they are reverse of each other, right? It's all the reverse process, right? The key the same. In public key cryptography, the algorithm is the same, but the key is different in both cases. So the convention is we call the private key D for decryption, and the public key we call it E for encryption. That actually, I just want to mention that this is just a convention to differentiate between the two keys because we cannot call them K. Um, so we call one D and one E, but that doesn't mean one has to be always dedicated for decryption and the other one is dedicated for encryption. In fact, we can use either one of them to do both, right? So keep that in mind. All right, so this is the algorithm, or this is the concept again. We have the sender has a plain text, pass it through the encryption algorithm with one of the keys, and then that generates the plain text. That generates the ciphertext. The ciphertext is received by the other entity. Use the same encryption algorithm, but with a different key. All right. Now, in public key cryptography, we consider the encryption and decryption keys as inverse of each other, right? That will be clarified later, but the inverse with the secret key cryptography, the algorithms are inverse of each other. The key is the same. Here, the algorithm is the same. The keys are inverse. All right. The public key cryptography is something new, relatively new, and based on mathematical advances in mathematics. We know more about prime numbers. We know more about random, how to generate them, how to do uh, modular arithmetic. So it's a relatively recent invention. But the problem is with this type of cryptography is actually much slower than the traditional secret key cryptography. It's about 1,000 times slower in some estimates. So imagine if you are encrypting a document and it takes for DES 1 second to do it, then it will take 1,000 seconds to do it um, with public key cryptography. That's actually limits the use of public key cryptography. Um, However, in theory, it has all of the applications of the private key cryptography and some more. So we have actually a lot of applications for public key cryptography and modern networking, especially modern client-server applications. They benefit from public key cryptography tremendously. And I think I cannot imagine um, having all these advances in networking without having public key cryptography. So we will see later how to avoid uh, or at least take advantage of public key cryptography, but in an efficient way, so we don't have to encrypt everything in a very slow, fashion. Uh, so one of the techniques that we actually avoid using public key cryptography um, is to use it to exchange keys or use it to at the beginning of the communication protocol that we want it to be secure, right? And then after that we will use traditional uh, secret key cryptography for that. Okay, so let's look at some of the applications now. The applications here, um, we see we have similar to secret key cryptography. The main application is to secure information over insecure channel. So we can encrypt something, send it, the other entity take it and decrypt it. Right. So in this picture here, you see that we have two keys. Always have two keys. So let's say Alice publishes her key to everybody. Say, well, anybody who wants to communicate with me, here is my public key. Write it down. Right? But she keeps the other key private. She publishes one, keeps the other one. Nobody else takes it except her. So now, let's say she wants to send something encrypted, or better yet, somebody wants to send something encrypted to her. So that somebody encrypts a message with her public key, send it to Alice. Alice takes that message and decrypt it with her private key. Right? Here, actually, the picture shows the reverse. The picture shows that Bob has Alice wants to sending something encrypted to Bob, so she encrypts it with Bob's key, public key, and he takes the message and decrypt it with his own private key. So let me give you another example just to illustrate. Let's say I want to communicate with, or I want the students to send me their assignments encrypted, so only me can see the assignment. So here is me, right? Here are students, all right, and maybe multiple of them. All right, so I am going to publish my public key. Say anybody who wants to send me their assignment, here is my public key, you can use it. So everybody knows my public key. The private key, I keep it to myself. Right? So student A take their assignment, let's say assignment A, encrypt it with my public key and send it to me. Now I can take the whatever the encryption is, and decrypt it with my own private key, and I'll get the assignment. The second person will do the same thing, and the third person will do the same thing. So here is the advantage. The advantage is all of what I needed is two keys. Even if the class has 50 people, all I need is two keys. And I need to share one key among everybody. Everybody gets it. And I'll keep another one to myself. Don't share it. So that eliminates one of the issues with secret key cryptography is we have to have the key secret. We have to share it with somebody, right? To be able to encrypt stuff. But we have to keep it secret from everybody else. So we have this dilemma that we have to share it, but also we have to keep it with everybody else, from everybody else. In public key cryptography, one key I don't have to share at all. I can keep it to myself. Everything else, the other key is, you can publish it in a newspaper if you want to, or put it on a social media, right? And the other advantage here is that neither one of these students can see the other. Let's say B take hold of the assignment from A. They cannot decrypt it because the decryption does not work unless you have the other key, unless you have D, right? So this operation does not work. You won't be able to decrypt the message unless you have D, right? So that's great. And now just to see in practicality, what do we do, or where is this working? Well, every time you go and use a website that uses the protocol HTTPS, you're doing exactly the same. You're getting the key from the public key from the server, and you are encrypting the message, your communication with that server with their public key, and then send it back, and they use their private key to decrypt the message from you, right? Every time you use an application like this, you're actually using um, well, it is more detailed than that. Remember, I said public key cryptography is slow, so there is a more involved, and we don't want to spend too much time talking about protocols. But this is one of the reasons we're using this public key cryptography. In fact, actually, we use public key cryptography only at the beginning of the transmission when we agree on a key, uh, secret key, and then we use secret key. But just hold that thought until we get to discuss protocols at some other course, right? But the principle is valid. Now we can use the same technique to store something in a file in a media, right? So we can store it with one key and decrypt it with another key. Because of the public key, private key thing, you can actually ask somebody to store a file for you. You give them your public key, they will encrypt any file and store it for you, and you can retrieve it with your private key. Or you can use secret key cryptography to store the file, but the key itself, you encrypt it. So you encrypt the key with a secret key and maybe give the public key to a lawyer and say, well, um, save that for you. Well, this is probably my will, and if I die, you can decrypt the file using my public key. So even though he doesn't know your key, but he knows how to decrypt your key and then take the key and decrypt your files for you, right? So that's another application that's uh, possible with public key cryptography. Authentication is another application. So in authentication, because let's say Alice and Bob um, Alice and Bob, let's say Bob publishes his public key for everyone and keeps their private key. So Alice can take Bob's public key and encrypts a random number and send it to him as a challenge. Say, if you are really Bob, well, here is the random number. Now, if you're truly Bob, decrypt it and send me the actual number that I encrypted. So because Bob has his private key, so he decrypts the challenge and send back the original R, the original random number to Alice. Alice compares the numbers and they are the same. So, okay, now I believe that you are Bob. Right? So that's not really different from what we saw in secret key cryptography, except that we don't exchange the key. Alice and Bob, they don't need to go coffee shop and exchange key out of band here, right? No, Bob can publish the key over the communication channel. Say, anybody wants to talk to me, here's my public key, right? And then later to identify me as the true um, identity, you can challenge me with that public key. Another application for public cryptography is the digital signature. This is something similar to the MAC that we studied, or the CPC residue that we studied in the previous chapter. Here, we take a message, we hash it. Hashing means take a message and reduce it to a fixed size. So take any file, any message in theory, and reduce it into a shorter but and fixed length message. So everything translates to 256 bit, for example. That will be the hash. And then we encrypt the hash with our secret key. And then we send the message with the encrypted hash. The encrypted hash, now we call it digital signature, right? So if you receive a message with me with my digital signature, what do? You know my public key, so you hash the message, or actually you hash the message and you decrypt my signature, and if the hash that you get and the decrypted message are the same, you know that it's coming from me, and you know that it's not tampered with. So there is actually two benefits. The first benefit is you know that the message was not changed. And the second benefit is you know that's from me. Why you know it's from me? Because I'm the only one who can generate it. So if I draw this again, I think you have this drawing in the notes. Somewhere here, maybe later, in the next or in the coming pages. But let me draw it in another way here. So you have this is the plain text, and you hash it. So you generate hash, which is shorter, right? You encrypt the message with one of the keys, usually your private key, and so that generates the signature. You send the message with the signature by both. So the receiver takes the plain text and the signature, right? This is the encrypted, right? The encrypted message. And they generate the hash from it. This is signature. This is the hash. So the signature itself is encrypted with D. The receiver will take this and decrypt it with E, the public key. Now the result will be the hash. If these two are equal, then, well, we know that this message here, the plain text, is okay, right? It's not being tampered with, and also it came from the person who claims to be the sender, right? Not somebody else who intercepted it, right? So that's what we mean by digital signatures. It's not digital signature is like the one that it's not like a sign, you know, that's just a picture of a signature, but the digital signature is based on public key cryptography, right? Okay, so uh, unlike secret key cryptography, where all the algorithms do the same thing, DES, 3DES, AES, and IDEA, all they do encryption. Yes, the applications can be different. So we can use encryption to encrypt a message, and we can also use the encryption algorithm to generate um, uh, similar to the signature, right? Similar to the MAC or the CBC residue that we talked about. But they're all do the same thing. They encrypt. In public key cryptography, we actually have different algorithms for different applications. So here the RSA is one of the famous algorithms that do digital signatures and mainly encryption, right? Um, we have DSS that does digital signatures. We have Diffie-Hellman is very famous algorithm that allows both parties to create a secret key without even actually sharing it uh, over the same channel, which is great, right? And then finally, we have something called zero knowledge proof systems. We don't have an example of that in this chapter, but uh, this is this is actually cool uh, uh, application where um, we can tell people that we know certain information without actually telling them what the information is, but we prove to them that we know the information. So we'll talk about that when we get to it. Okay. Public key cryptography is based on modular arithmetic, right? So we need to understand a few things in modular arithmetic before we can continue explaining some of the algorithms that we want to talk about. So as a reminder, modular arithmetic is or gives us the remainder of a division. So if I divide 7 by 3, the result of the division is 2, right? And the remainder is 1. So now we are really interested in the remainder, right? So in mathematics, this operation is represented by mod, and other languages can be represented by different symbols. So in Python, it's represented by, let's say, 7. This is percentage simple here, 3, so that gives us 1, right? So a few things that we need to understand. Um, the first thing is what's called the uh, congruent numbers, which is, well, let's say if any two numbers can be um, divided by modulus m, and then the result will be identical, will be the same, then we will consider them belong to this set, right? We'll consider them these congruent numbers. I hope I am pronouncing it right. So in that case, let's say 1 mod 12 is 1, 13 mod 12 is still 1, 25 mod 12, 25 mod 12, it's still 1. So all of these are considered, not identical, but similar. The other concept that we need to understand is the inverse. This is really important. So in mathematics, if I multiply 8 by 1 over 8, I get 1. So in this case, the inverse of 8 is 1 over 8. Right? In modular arithmetic, the inverse, if I multiply A by B mod, let's say C, and I get 1, I consider A is the inverse, is B inverse, right? Or I consider B is A inverse, the inverse of A, right? So these two must be inverse of each other. Otherwise, when we multiply them, we won't get 1. So that's for modular arithmetic. Does that mean that 5 multiplied by 1 of 5? No, actually, it may not be this way. Let's say there are a few examples here. So one of them is 3 multiplied by 7 mod 10 is 1. So obviously 3 is not equal 1 over 7, right? But these are still 7 and 3 are considered inverse of each other, because in modular arithmetic, when we divide and take the modulo of 10, take the remainder of 10, the result is 1. So 3 by 7 is 21. Divide by 10, the remainder is 1. Right? So that's something very important to understand. And actually, that affects all of these operations. So when we do 22 plus 8 mod 12, now consider these are the result, or the addition of 22 plus 8 is 30. So 30 mod 12 is 6. If I do subtraction, same thing, 25 minus 8 mod 12, so that's 17 mod 12 gives us 5. We do multiplication, 5 by 8, that's 40 mod 12, we get 4. All of these are understandable, right? But there is no such thing as division in mod operations. So 6 divided by 5 mod 7 is not 1 point something something, right? No, it's actually, it means that here it's 6 multiplied by the inverse of 5. So this is 5 to the power 1 minus 1. Again, this is the convention. It's not really 1 over 5, right? So you have to understand that we mean by that it's the inverse of 5, right? So how do we solve this? How do we know what is the inverse of 5 in modular arithmetic? All right, so to do that, we have to find something that we can multiply by 5 and result in 7. So we are looking for A, let's say A multiplied by 5 mod, what was the 7? I think it was, actually mod 7 equal 1. So we're looking for a number that when we multiply it by 5, mod 7 equal 1, right? So let me write down the operation again just to have the whole thing in one place. So we're looking for the operation 6 divided by 5 mod 7, right? We want to know what the answer is. 6 divided by 5 mod 7 equal something. So we need to find the solution, right? So here, this is equivalent to 6 multiplied by the inverse of 5 mod 7. We don't know what the inverse of 5 is. It's not 1 over 5, right? It's in modular arithmetic, it's not 1 over 5. So what is it? So here we go back to this formula here. So A multiplied by B mod C equal 1. This means that one of them is the inverse of the other. So I want the inverse of 5 here. So this must be the inverse of 5. A must be the inverse of 5, right? So what is it that I can multiply with 5 and I get the result mod 7 is 1. Okay, so the short answer is 3. 3 multiplied by 5 gives us 15 mod 7. Now 15 divided by 7 is 2, right? And the remainder is 1. So that must be the inverse of 5. How did I get that? Well, so there is a long answer and short answer, or the tedious answer and easy answer. So I can try all possibilities. I can try 1 multiplied by 5, 2 multiplied by 5, 3 multiplied by 5, and get the modular for each one of them until I hit the number that actually gives me the result. All right, so so that's the long way and the tedious way. But how many numbers I should try? Well, it turns out to be ranges from 1 to whatever this number is minus 1. So in general, A has to be from 1 to C minus 1. Right, C here in the top that you see. So we don't have to try many. So we can try 1 multiplied by 5, 2 multiplied by 5, 3 multiplied by 5, until 6 multiplied by 5. What happens if I multiply 7 by 5? Well, you start repeating yourself, right? 7 multiplied by 5 is 35, divided by mod 7, you get 0, right? So you start repeating the cycle. So we need to try only from 1 to C minus 1, as you can see here. Actually, you can start from 0, but 0 doesn't. You can try 0 will work only if you have mod. Actually, it probably doesn't work at all. So I'll check the notes and see if 0 actually available or a possible number there. Okay, but C minus 1 good if the number is small, right? But what if the number here mod 3 to 6? Okay. So I have to try from 1 to 3 to 2, 3 to 5. That's a lot of numbers to try. All right, so we have a solution for that. We have a different solution for that. But for the small numbers that we will try, you just give it like a trial and error until you find the answer. And the answer in this case is 3. We obtained it by trial and error. Okay, so now that we know the inverse of 5 is 3, so we can go back to our original question here and replace the 5 inverse with 3, so 6 multiplied by 3 mod 7, so that's 18 mod 7, it will give us 4, and that will be our answer. Okay, so there is another condition before we continue. This only numbers that are coprime can have modular inverse. Okay, so what does that mean? What is coprime? Coprime is the, or sometimes the, we'll call it relative prime, are two numbers that are not prime, or they don't have to be prime numbers, but they don't have any common factor. So here, 5 and 7, they don't have common factor, so we can find an inverse to 5. But we cannot find an inverse to, let's say, a multiplied by 3 mod 6. There is no inverse to this one because 3 and 6 are coprime. Are not coprime. Not coprime. Why? Well, because 3 has a factor 1, 3, right? It's a prime number. 6 has a factors 1, 2, and 3. So here we have a common factor. This means that 6 can be divided by 1, 6 can be divided by 2, and we get 3, or 6 can be divided by 3, we get 2. So these are the factors of 6. These are the factors of 3, and there is a common factor. So 6 and 3 are not coprime. 5 and 7 are coprime. Why? Because we don't have any common factors. This can be divisible only by 1 and 5, and this can be divisible only by 1 and 7. Right. These are also prime numbers, but sometimes we have coprime that are not prime numbers themselves. So generally speaking, they don't have to be prime numbers. And we will talk about this in the next page. But just as a reminder, modular arithmetic is linear operation. So if I do a plus b mod m, I can do this the same thing by saying a modulo m plus b modulo m, and the result modulo m, we get the same result. Right? And for the minus will be the same, for the subtraction, for the multiplication will be the same. Now, as I said before, the division is not really defined. We don't have a division in modular arithmetic. The division is what we saw here, where we have to find the inverse. So, and from algebra, we know that a to the power x multiplied by x to the power, x to the power a multiplied by x to the power b, that's equivalent to x to the power a plus b. So here, I know you know this, but let's say x to the power 2 multiplied by x to the power 5, that's equivalent to x to the power 7. And same thing if I do x to the power 2 to the power 5, that's x to the power 10, right? Multiply 10 by 5. So keep that in mind when you do these operations, right? Because sometimes we need to simplify the modular arithmetic, right? And we need to use these identities to solve some of the complex problems, especially the ones that you cannot handle using a calculator. So we need to simplify it a little bit. Okay, so as promised, we need to talk about coprimes and primes. In fact, the whole public key cryptography is based on understanding prime numbers, especially large prime numbers, right? without knowing prime numbers, we won't have public key cryptography. So they play essential role in public key cryptography. So prime number is the number that has only two factors, so it can be divided only by itself or 1. So 7 is a prime number, right? 9 is not. 9 can be divided by 3, so you get 3. 11 is a prime number, 12 is not, right? So that's understandable. Small prime numbers we can find them very easily. 1, 2, 3, 5, 7, 11, and 13, and so on, right? But the challenge is to know the large prime numbers, right? And these are the ones that we need for public key cryptography are 64-bit long, 512-bit long, so they're not the small ones, right? Okay, coprimes are also important. So what is coprime or relative prime? So here's the example. 7 is prime number, 45 is not, because I can break it down into factors. So 45 is the result of multiplying 3 by 5 by 3. So 3 by 5 is 15, by 3 again is 45. So I can factor it, and these factors are 3 and 5. 22 is a number that's not prime because we can factor it as well. 55, we can factor it into 1, 5, and 11. 22 and 55 are not relatively prime or not coprime. Why? Because they share the same factor, 11 and 11. 55 and 32 are coprimes. Why? Because we don't have any common factor except 1, right? So 55 can be divided by 5 or can be divided by 11. 38 can be divided by 2 or by 19. So they don't have any common number or factor except 1. Now, take 22 and 38 are not coprime because they share factor 2. Take 45 and 55, they're not coprime because they share factor 5. But 45 and 38, they are coprimes because they don't have any common factor in between. This is 135 and this is 125, so the only factor is 1. So the 45 and 38 are coprime. Okay. All right, a few things that we need to keep in mind as well is these theorems in modular arithmetic that says, well, if I have m to the power p minus 1, where p is a prime number and m is something smaller than the prime number, right? So m to the power p minus 1 mod p equal always 1. So the example is 7 to the power 10. So 11 is the prime number. 11 minus 1 gives us 10. So that's p here that we use. And m is smaller than p, right? So 7 to the power 10 mod 11 equal 1. How is that useful? Well, imagine we have large numbers, right? 7 to the power 10, that's a huge number. If I want to divide it by 11, well, I may not have maybe modern calculators will do it, but I mean, sometimes these numbers you cannot put them in a spreadsheet. You cannot do these operations in spreadsheet. So some of your calculators are more powerful than Excel spreadsheet. So you have to simplify these things, use them for simplification. Another observation here, another theorem is that if I take two prime numbers, multiply them, so that's n. So m to the power p minus 1 q minus 1 mod n equal 1. This is actually something that we need to understand very well, for the next algorithm that we study. If I multiply both sides by m, m here and m here, we get the result is now, of course, you add m here, so you add 1 to the exponent, right? So, all right, so we have these basic um, modular arithmetic principles. So now we want to use them for public key cryptography. So the first algorithm is one of the most famous, and it is used for encryption and decryption, and it's called the RSA algorithm, called RSA because the inventors, right? So the inventors created the algorithm, they named it after themselves, and the algorithm works. First of all, we need to understand how to generate the keys. So that has two aspects. And in fact, actually, in public key cryptography, the algorithm itself is simple modular arithmetic. The key is the challenge. While in secret key cryptography, the key is just a random number. The key, we can generate a random number. Just what it, if somebody tells me that I need 64-bit key for the DS, or 56 in fact for the DS, I can just generate any random sequence of bits of 56-bit length. So that's not the challenge. And the algorithm, finding the algorithm that does the confusion and diffusion and substitution and all of that, is the challenge. Here, actually, the challenge is to generate the key that's strong enough. The operation itself is simple. All right, so the first bit is to how to generate the key. The second aspect is how we do the encryption, which is the easy part, the encryption and decryption. All right, so how do we generate the keys? So we need two keys, remember. So the first step is to have, we need to come up with two large prime numbers. We'll call one of them P and the other one is Q, right? And as I said before, that was the main principle behind public key cryptography, is coming up with all of these big, large um, prime numbers, which, by the way, they have to be big sizes, right? 64-bit, 128, 256, and these are large numbers. We will deal with only small numbers in this course because we cannot handle those large without computers, but small numbers will be enough to illustrate the principles, right? So come up with two large numbers, P and Q, multiply them, we get N. We keep N in mind, and then step 2, we will find a number that is, we call it E. That's our actually the public key, or one of the two keys. The number has to be between 1 or larger than 1, so 2, 3, 4, and so on, and smaller than P minus 1, Q minus 1. Any number in between. But there is a condition. The condition is another condition. The first condition is it has to be from 1 to P minus 1, Q minus 1. But the other condition is to must be co-prime to the number P minus 1, Q minus 1. Right? All right, so that's a little bit of a challenge, right? So finding E, I can say 3 is good, 4 is good, but I have to find a number that must be co-prime to the value P minus 1 multiplied by Q minus 1. If I find something like this, then that is considered my public key. All right. I said before that we need to exchange the public key with everyone, keep the private key to ourselves. In fact, actually, what we need to exchange is the N and E, right? So we need to send everybody N and E. So the tuple, the key actually tuple with N and E. Okay. And how about the other key, the private key? So the other key has to be an inverse of E mod P minus 1 Q minus 1. Here comes the inverse that we talked about earlier. Right? It can be written this way. So I can write it ED, so E multiplied by D equal 1 mod P minus 1 Q minus 1. I can write it this way, or I can write it this way. So ED mod P minus 1 Q minus 1. This is equivalent to writing it ED, or let's say these two forms are equivalent. In fact, actually, I forgot how to, yeah, mod 1. So I put the mod in the wrong place. I like this one better. I remember it easily, right? So here equal 1. Okay, so let me repeat that again. First, we need to find n, which is p, q, two large prime numbers. And then we have to find e that is greater than 1 and smaller than p minus 1, q minus 1. So that's step 1, that's step 2. The other condition is e must be co-prime of p minus 1, q minus 1. And the third example, or the third step, is finding D, where D is DE is 1 mod P minus 1 Q minus 1. Or if you want to write it this way, DE mod DE mod P minus 1 Q minus 1 equal 1. Okay. So how do we find co-prime? Trial and error is one of them. But we also, if you are using Python, there is built-in, in the built-in module math, there is something called GCD. GCD function, you can, if you use it, let's say if you want to find the coprimes of 9, it will give you all the coprimes up to 9. So 1 is a coprime of 9. 2 is a coprime of 9, 4 is coprime of 9, 5, 7, and 8, all coprimes of 9. So that's easy, right? So I can plug through 3 to 7, and it will give me all the coprimes from 1 up to 3 to 6. All right. So before I continue, let's use some simple numbers to illustrate this example, all right, or this procedure, because now we need to put this into something that is we can understand. All right, so let's come up with n equal pq. Now the actual RSA algorithm requires two large numbers. Why we need two large numbers? Because everybody can guess small numbers. And also because we need large numbers because the message size has to be smaller than the key. And we will see why when we get to the second part of this algorithm. But if we start with a smaller number, then our message will be small too. So we need something large, right? Okay, so but for example, let's assume that P is 5 and Q is 11. So both are small prime numbers. This is prime and this is prime. All right, so N will be 55, right? Then we need to find E. E has two conditions. The first condition is E must be 1 and smaller, greater than 1 and smaller than P minus 1, Q minus 1. Right. And the second condition is that E, D, no, not yet, E and P minus 1, Q minus 1 coprime. Okay, so what is P minus 1, Q minus 1? So let me put it this way. E, so P minus 1 is 4 and Q minus 1 is 10. So E must be somewhere between 1 and 40. Okay, if I use 5, it doesn't work because 45 and 40, they share the same factor, which is 5. If I use 6, well, they share the same factor as 2. 7, well, 7 sounds good. 7 is also a prime number, so we guarantee that it's not co-prime with 40 because we cannot divide something. So let's call E is 7. Okay, so now our third step is to find D. And the condition here is to have DE mod P minus 1, Q minus 1 equal 1. So we want to find something that we multiply with 7 mod 40, we get 1. So D here is the inverse of of 7. And from the earlier of the recording, I said that we can do trial and error, right? So we can try all the numbers 1, 2, 3, up to 39. So what is the number that we can multiply by 7 and we'll get 1? All right, so I'm gonna pause, find the solution, and come back. Okay, as it turns out that the number 23 is the inverse of 7. All right, so if I multiply 23 by 7, I get 161 mod, so modular operation is here, so mod 23 multiplied by 7 mod 40, I get 1, right? So now D is 23. Okay, so my public key that I will exchange with everybody else is N and E, which is 40, sorry, not 40, 55, and E is 7, and the private key that I will keep, private, is N and D. That's 55 and 23. Okay, so that's the operation that I need to come up with public key and private key. Right. So let's do encryption. So the encryption algorithm, as I said, it's very simple. C, the ciphertext, equal P to the power of the encryption key mod n. So when somebody gives me the public key, I can encrypt any message by taking the plain text, convert it into a number, of course. So anything that we need to convert it into a number, take the power to E mod n, right? So the operation itself is simple, but why did I say it takes sometimes 1,000 times more to calculate this than simple secret key cryptography? Because imagine you have a 64-bit key to the power of another 64-bit key, right? Well, it's not easy to calculate, right? So, but for small numbers, we can do it in a simple calculator, right? So let's say the inverse will be P equals C to the power D mod N. So the inverse exactly, I mean the same algorithm, just using two different keys, right? Same algorithm, two different keys. All right, so the message has to be always smaller than N. So let's take something, let's say the P is 6, right? So C P to the power E, so that I'm gonna encrypt it, and mod N. So P is 6 to the power E, which E is 7, mod 55. So let's use the calculator here. Six to the power 7 mod 55, so 41. So that's our ciphertext. All right, so if I want to get back the plain text, so that's C to the power D mod N. So 41. Notice here that now we are starting to use really big numbers, and that's where you need to use those identities to simplify it. If you have to, we'll do some exercises about simplifying these numbers, but I think my calculator will handle these numbers. But sometimes they are going to be too big to handle, so you need to simplify them a little bit. All right, so 41 to the power of 23, that's a very, very large number, mod 55, so you get 6, which is what we started with, right? So that means that we got the right public key and the right private key. Now, before I finish this example and this topic, do I really need to always encrypt with E and decrypt with D? No, I can actually do the opposite, and it will give me the same result. So that's not in the notes, but I need to emphasize this. So let's say sometimes it's necessary to encrypt with the private key, and so that the other will decrypt with the public key, as we talked about the digital signatures. The digital signatures actually work by encrypting the hash with the private key and let other people decrypt it with the public key. So I'm gonna flip. I'm gonna use use D for encryption, right? And it will work fine. Right? So we have 6 to the power of 23 mod 55. So we will get 6 to the power of 23. So we get 51. That's our ciphertext. So the plain text again will be C. So 51 mod 7. 51 to the power of 7 mod 55. So to the power 7 mod 55, and we get 6, which is the original. So that proves to you that we can use either one of the keys for encryption and the other has to be for decryption. So if I use E for encryption, we encrypt with D and vice versa, right? So the E and D is just for convention because I cannot call them both E or K, or so that's the convention. All right, now I went offline a little bit, tried did some trial and error to figure out the inverse of 7. But the inverse of 7 for large number will be really difficult if I'm gonna do trial and error. So actually, there is an algorithm called the extended Euclidean algorithm that does that for you. So you just need to supply, let's say if you want to, you find the solution for this, PA mod M, which is equivalent to ED mod P minus 1, Q minus 1. So if you want the solution to this, you just give it the A and M. So give it one of these and M. It will give you B. It will give you the inverse, right? And this is the it's based actually on the function that we have here, GCD, right? So you can use this if you have Python, run Python, give it any of these two. So you give it either P or Q and M here, and it will give you the inverse. So here the inverse of 5 mod 72, it's 29, right? And here is another example. Let me see. I have actually, yeah, we have an example here that uses. I tried 5 and 11 as P and Q. Here is another example where we have P is 7, Q is 13, so N is 91. We selected 5 as E because it fits the conditions, and then we calculated D by trying to solve this formula, right? So we need to multiply something by 5 mod 72, we get 1. So if we do trial and error, it will take us some time, 1, 2, 3, 4, until we reach 29. But if we use the Euclidean algorithm, then we can find it easily. And so now we have the public key is 91 and 5. 91 is the N here, and the 5 is our E that we generated, and the private key is the 91 and the 29. Okay, so this is how we solve how we do encryption and decryption. Right. Okay, so that is one of the main applications of public key cryptography. So next, we're going to talk about digital signatures. So as I mentioned before, when we talk about digital signatures, uh, we talk about, there are two goals. First one is the message. We ensure that the message is not being changed, is not being altered, right? The message could be sent as plain text. It doesn't have to be encrypted, uh, but we make sure that we don't or nobody else change it. Another goal for digital signatures is to um, identify the sender, so we know who it came from, right? And also we will have this goal of security, which is the non-repudiation, um, by making sure that the sender does not really later claim that they didn't send it, right? So I send you a message saying we have a meeting, and I will send it to everybody. I want to make sure that nobody changes it. And also, when you receive it, you know that it's coming from me and not somebody else. And later, let's say you're in a bank application or some legal application where uh, you want to make sure that this message actually came from the person, and the person cannot later say, no, I didn't send it. So that's the goal of the regular signature, right? So when we sign a paper uh, with our regular signature pencil pencil and paper thing, this is what we actually do. We put our signature on a paper to say that this is what we agree to, or this is what we intend to do, and later this signature will be used to identify us in any legal uh, manner. So we do this with digital signatures, and we use public key cryptography for it. So the digital signatures have several algorithms. RSA is one of them, actually, and there's digital signature algorithm and the elliptic curve DSA. So since we have studied RSA, so we're not gonna study any other algorithm for this manner. We just need to make sure that we understand the process. So if Alice wants to digitally sign a message to Bob, she performs these actions. First, she generates the message. We'll call it a message digest or message hash, right? And for the message hash, we need algorithm. These are the things that we will talk about in the next chapter. But right now, as I mentioned earlier, a hash is, or the hash algorithm takes any length message and shrink it down to a fixed size message. So the fixed size could be 128-bit, could be 256-bit, and so on. That message, or the hash, we encrypt it. Alice encrypts it with her private key. And this is an example of encryption with the D key, not the E key, as I mentioned before. Alice appends the signature to the plain text and sends both. So Bob receives the plain text message, decrypts the signature, so now he has the decrypted hash. And he also used the plain text to generate his own hash, and then compares the two hashes together. If the two hashes are the same, then he knows that the message is actually authentic, came from Alice, and wasn't changed. So here's a diagram. Plain text goes to the hash function. Then the hash function is encrypted using the sender's private key and the digital. This is the digitally signed document, which includes both the plain text and the signature. And it goes through the network. It comes to the destination. Here's the same digitally signed document. We take the hash of the plain text part and we decrypt the signature part, and if both are the same, then we're good. Okay, so this is a Python code that does this for you, and you see here this is the original message and this is the signature. The signature looks like bigger because actually the message is always changed to the fixed size. So if the message actually less than the hash, it will be appended. We'll add spaces to it. Right. Okay. The next thing that we need to study is something called Diffie-Hellman algorithm. This algorithm allows two parties to exchange a key without actually sending it over any channel or without even sitting together and sharing it, right? All right, so how is that possible? Well, let's take a look at the algorithm. So Alice picks numbers B and G. P is large prime number and G is a number less than P, right? And Alice sends both numbers to Bob. So let me put this on the side here, or try to work both documents at the same time so we can do the algorithm while illustrate it at the same time. So here is Alice and Bob. All right, so Alice picks two prime numbers, one prime number and a number that is smaller, so P and G, and sends them to Bob. Okay, Bob and Alice at the same time, they come up with their own secret number. They just get a random number. So Alice come up with something of her own, and Bob comes with a secret of their own. So these are not shared. They just keep them to themselves. Alice and the same time Bob, they calculate TA, which is G to the power of SA mod P. Bob does the same thing, calculates TB GSB mod P. Then Alice and Bob, they exchange these numbers. So Bob sends his own, the number that was sent, that he created, and Alice sends hers. Okay, so now Alice calculates K, which is the number that she got from Bob raised to her own secret key again, mod B, and Bob calculates, takes TA that he got from Alice and raise it to his own number, mod P. And these two are going to be the same. So this will be the shared key that anybody who is sitting here listening or sniffing the traffic won't see. So Alice and Bob come up with their own key without actually sharing it. And that can be used for secret key cryptography. So as I said when I started this recording, because public key cryptography is much slower than secret key cryptography, sometimes we use it only at the beginning of the communication, and then we come up with a shared key, and then we will use that key for the rest of the communication. So actually, this is one of the algorithms that usually we use to have two parties who probably never met ever in their lives, or two entities, computer, like client and a server, not even humans, right, to share a key without actually sharing anything on the channel itself. That's not the only way. We can do other ways. We can do other techniques, but this is one of the ways that we can use. Okay, so what was the magic behind this? How did we come up with the same key? Okay. So you can see here from the notes, TB to the power of SA is actually this G to the power of SB to the power of SA. So that's G, SB, SA, right? If I flip them down, so reverse them, so that's GSA to the power of SB, which is TA to the power of SB mod P. So this was the number that was taken from Bob, and Alice used her own secret, and this was the message that came from Alice, and Bob used his own secret. So both of them are the same because of this. Now, as with all cryptography, we assume that this technique is secure because nobody will be able to calculate SA and SB in a reasonable amount of time. Both of them were generated separately by Bob and Alice, the secret numbers, so they are never exchanged in the channel. So for someone to try to guess them will be hard, right? And they have to guess a lot. Okay, so let's use an example here where B is 23 and G is 7. Okay. So let's go back to the example. So G or P is 23, and which is a prime number, and G is 7. Okay, and we can guess any numbers. So we'll guess SA and SB of our own. So Alice and Bob, Alice sends P equal 23 and G equal 7. So what we do next, Alice comes up with her own secret number. So let's say 3. Keep the number small. And Bob comes up with his own secret number. Let's say 4. Right? So what do they do next? They take G to the power S, G to the power SA mod B. So G, or let's use the numbers right away. So 7 to the power 3 mod 23 and 7 to the power 4 mod 23. So that will give us just use the calculator here. So 7 to the power 3 mod 23, get 21 here on the side. So that's our TA. And on the other side, 7 to the power 4 mod 23, that's 9, which is TB. So now Alice sends her TA equal 21 and Bob sends his TB equal 9. So Alice take TB and raise it to her own SA, so 9 to the power 3 mod 23, and Bob does the same, so we're supposed to get the same number here, okay? So 21 raised to 4 mod 23, so 9 to the power 3 mod 23 gets 16. That's K. And 21 to the power 4 mod 23, that's 16. So we actually got the same K value, which this is how we verify if this is a question in an assignment or a quiz. This is how you verify that you did everything right. You have to get the same number. If you get two different numbers, then you must have done something wrong, right? So there are other possibilities that I'm not going to consider here. So let's say if SA and SB are the same, what happens, right? Try it and see what happens. So there are some cases where these things don't work or they don't generate a good key, right? That's why these numbers has to be big. The more big the number is, or the larger the number, the less likely that we will end up with the same number. All right, so there are some cases where this doesn't work, and also there are some cases where this can be discovered, right? So if you read the literature, and I think I have something that I can share as well about the strength of some of these algorithms. So they have their own weaknesses, right? So there are modifications. We are looking at the simplest and the straightforward, but there are some modifications, and I shouldn't say modifications, but enhancements. And the final thing that we need to talk about is the zero knowledge proof system. So there is no special algorithm here, but the idea for the zero knowledge proof system or the application is, let's say Alice knows a secret and she wants to sell it to Bob, right? I have something to, I have to something to, I have really something that's worth your while, and I want you to pay me before I tell you. Well, Bob say, well, tell me. I'm not gonna pay for something that I don't know what it is. So now we have an impasse. We have, well, Alice is not gonna give her secret without payment, and Bob is not gonna pay without knowing the secret. So there is a way to prove that you know something without actually telling anybody what it is. And that's the zero knowledge proof system. And it's explained easily this way and interestingly enough. So let's say there is a door here, and the door can be opened by lock, like the 4-digit number or 5-digit number, right? So Alice, Bob, right? Uh, Alice tells Bob that she knows the secret. Bob says, "Well, prove it." So Alice can walk around this, opens the door with her secret, and comes back. Right? So now Bob knows that Alice knows the secret. She's not lying, because otherwise she wouldn't be able to pass through the door. The door is locked with a secret lock, secret password. So now this kind of systems that we call them knowledge proof systems, and they are now this is the illustration for it, but you can have certain ways to mathematical ways to show that you know something without actually uh, revealing what it is. Right? So that concludes the chapter 6, and I will see you in the next chapter, and thank you for listening.